What if we told you that every time you look up at the night sky, you're witnessing the story of birth and death that's been unfolding for billions of years? It's the epic tale of stars, and it's one that's been captivating humans for centuries. From the fiery birth of a star to its spectacular demise, every moment is a cosmic wonder. So, join us on a journey through the universe as we explore the birth and death of stars. Trust us, you don't want to miss this. Watch now and prepare to be awestruck. Stars don't live eternally. They have interesting histories of becoming, and they die. They are the very material we are made of. What is more, they produce this material in the first place. We are. It is already a cliché. Stardust, born from exploding, dying stars. How are stars born? Early in the history of the universe, before stars and planets existed, giant clouds of hydrogen and helium began to form. Slowly, these clouds collected enough mass for their gravity to form. This created extremely dense balls of gas. In other words, they formed stars. When a new star is formed, its core is exposed to very strong gravitational forces. This force is so great that the star is in danger of collapsing in on itself. Luckily, nuclear fusion provides the energy the star needs to push back against the collapsing core. Nuclear fusion is a process where the nuclei of two or more elements combine to produce nuclei of heavier elements. Nuclear fusion also releases energy. In the core of a newly formed star, hydrogen nuclei begin to fuse into helium. The inward pull of gravity and the outward push of nuclear fusion eventually balance out. For a time, hydrogen fusion prevents the collapse of the star. How long do we stay alive? A star's life expectancy depends on its mass. Generally, the more massive the star, the faster it burns up its fuel supply, and the shorter its life. The most massive stars can burn out and explode in a supernova after only a few million years of fusion. A star with a mass like the Sun, on the other hand, can continue fusing hydrogen for about 10 billion years. And if the star is very small, with a mass only a tenth that of the Sun, it can keep fusing hydrogen for up to 1 trillion years, longer than the current age of the universe. 7 main stages of a star. Stars come in a variety of masses, and the mass determines how radiantly the star will shine and how it dies. Massive stars transform into supernovae, neutron stars, and black holes, while average stars like the Sun end life as white dwarfs surrounded by a disappearing planetary nebula. All stars, irrespective of their size, follow the same 7-stage cycle. They start as a gas cloud and end as a star remnant. 1. Giant gas cloud. A star originates from a large cloud of gas. The temperature in the cloud is low enough for the synthesis of molecules. The Orion cloud complex in the Orion system is an example of a star in this stage of life. 2. Protostar. When the gas particles in the molecular cloud run into each other, heat energy is produced. This results in the formation of a warm clump of molecules referred to as the protostar. The creation of protostars can be seen through infrared vision, as the protostars are warmer than other materials in the molecular cloud. Several protostars can be formed in one cloud, depending on the size of the molecular cloud. 3. T-Tauri phase. A T-Tauri star begins when materials stop falling into the protostar and release tremendous amounts of energy. The mean temperature of the Tauri star isn't enough to support nuclear fusion at its core. The T-Tauri star lasts for about 100 million years, following which it enters the most extended phase of development, the main sequence phase. 4 is the stage in development where the core temperature reaches the point for the fusion to commence. In this process, the protons of hydrogen are converted into atoms of helium. This reaction is exothermic. It gives off more heat than it requires, and so the core of a main sequence star releases a tremendous amount of energy. 5. Red giant. A star converts hydrogen atoms into helium over its course of life at its core. Eventually, the hydrogen fuel runs out, and the internal reaction stops. Without the reactions occurring at the core, the star contracts inward through gravity, causing it to expand. As it expands, the star first becomes a subgiant star, and then a red giant. Red giants have cooler surfaces than the main sequence star, and because of this, they appear red more than yellow. 6. The fusion of heavier elements. Helium molecules fuse at the core as the star expands. The energy of this reaction prevents the core from collapsing. The core shrinks and begins fusing carbon once the helium fusion ends. This process repeats until iron appears at the core. The iron fusion reaction absorbs energy, which causes the core to collapse. This implosion transforms massive stars into a supernova, while smaller stars like the Sun contract into white dwarfs. 7. Supernova and planetary nebulae. Most of the star material is blasted away into space, but the core implodes into a neutron star, or a singularity known as a black hole. Less massive stars don't explode. Their cores contract instead into a tiny hot star known as the white dwarf, while the outer material drifts away. Stars tinier than the Sun don't have enough mass to burn with anything but a red glow during their main sequence. These red dwarfs are difficult to spot, but these may be the most common stars that can burn for trillions of years. D8 of an ordinary star. After a low-mass star like the Sun exhausts the supply of hydrogen in its core, there is no longer any source of heat to support the core against gravity. Hydrogen burning continues in a shell around the core, and the star evolves into a red giant. When the Sun becomes a red giant, its atmosphere will envelop the Earth, and our planet will be consumed in a fiery death. Meanwhile, the core of the star collapses under gravity's pull until it reaches a high enough density to start burning helium to carbon. The helium burning phase will last about 100 million years until the helium is exhausted in the core and the star becomes a red supergiant. At this stage, the Sun will have an outer envelope extending out towards Jupiter. During this brief phase of its existence, which lasts only a few tens of thousands of years, the Sun will lose mass in a powerful wind. Eventually, the Sun will lose all of the mass in its envelope and leave behind a hot core of carbon embedded in a nebula of expelled gas. Radiation from this hot core will ionize the nebula, producing a striking planetary nebula, much like the nebulae seen around the remnants of other stars. The carbon core will eventually cool and become a white dwarf, the dense, dim remnant of a once bright star. D8 of a massive star. Massive stars burn brighter and perish more dramatically than most. When a star 10 times more massive than Sun exhausts the helium in the core, the nuclear burning cycle continues. The carbon core contracts further and reaches a high enough temperature to burn carbon to oxygen, neon, silicon, sulfur, and finally to iron. Iron is the most stable form of nuclear matter, and there is no energy to be gained by burning it to any heavier element. Without any source of heat to balance gravity, the iron core collapses until it reaches nuclear density. This high-density core resists further collapse, causing the infalling matter to bounce off the core. This sudden core bounce, which includes the release of energetic neutrinos from the core, produces a supernova explosion. For one brilliant month, a single star burns brighter than a whole galaxy of 1 billion stars. Supernova explosions inject carbon, oxygen, silicon, and other heavy elements up to iron into interstellar space. They are also the site where most of the elements heavier than iron are produced.